In just 5 steps, I will show you how this short formula leads to one of the most famous principles in all of physics, the Heisenberg uncertainty principle. We'll start by asking, what exactly is this formula? Well, it goes by the name of the canonical commutation relation, and it's a fundamental relation between the position operator and momentum operator. In fact, it's so fundamental that in some textbooks you read, certain authors will take it as a starting point and then build the entire framework of quantum mechanics around it. The brackets here stand for the commutator, which is defined as equaling AB minus BA for any two operators A and B. So this relation tells us that the commutator of position and momentum is non-zero, and therefore the position and momentum operators do not commute. Okay, for the next step, we will use these two operators to define a new one. This new operator will be a linear combination of the two, where I is just the square root of -1 and alpha is some complex number. So this operator can now act on a ket to produce another ket. And since this whole thing is just another ket, we can take the inner product of it with itself. And by the definition of an inner product, this must be greater than or equal to 0. In step 3, we will utilize a few other aspects of the definition of an inner product. First, that it is linear in the second slot, so we can break this expression apart. Then, that we can take constants out from the second slot. And if we flip the values in the first and second slot, then the resulting inner product is the complex conjugate. Finally, by repeatedly applying these 3 rules, we arrive at this expression. If any of that was unclear to you, I encourage you to check out my video on inner products that I linked in the description section below. Okay, now for step 4. The momentum and position operators both correspond to observables. So by one of the axioms of quantum mechanics, they must be self-adjoint. This means that we can bring every instance of both x and p from the first slot into the second slot. Now the middle terms contain the commutator of x and p, so we can use the canonical commutation relation to replace it with IH bar. Taking IH bar out of the inner product reduces the expression to this. Okay, now we are ready for the last step. If you look closely, you should be able to recognize that this is actually a quadratic equation. So we can just use the quadratic formula to solve for alpha. This becomes especially simple since any quadratic that is always greater than or equal to 0 has no real solutions. So we only need to look for when b squared minus 4ac is less than or equal to 0. And doing some slight rearranging, we get this. Typically, our wave functions are normalized, so the inner product of psi with itself will be 1, and we arrive at our final expression, which is just the Heisenberg uncertainty principle, although in a slightly different form than you might be familiar with. But I assure you, they are equivalent.